All right, good afternoon. I'm John Rakovan from Miami University in Oxford, Ohio, and this next session is about a single mineral or mineral family, and that is apatite. The intersection of mineralogy with materials, biological, environmental, and earth sciences is beautifully exemplified by the wide range of applications and significance of apatite and apatite group minerals. And when we come to the discussion section, obviously there'll be time to ask questions of the speakers, but I would also like to come back, if we have time, to talking about this in general, not about apatite specifically, but there are many other examples of this. As scientists and teachers, having an arsenal of examples of interesting applications of minerals is something that we should all be carrying with us. And what I would like to do is ask the audience for new and interesting examples of where minerals are being applied in all areas of science and society. And the plan is actually to make a list and have something available on the MSA website for those of you who want to access something like that. And so before we start, before I introduce the speakers, we actually brought some teaching materials. Because the time at the end of the session is short, I'd like to pass them out now and then start the talks. And we have 3 baskets of fish scales, and these are from a fish called a alligator gar. If you've ever seen one, you know how scary it looks. But they're phosphatic. They're basically apatite. We also have something that Joe Pasteris will talk about in a little more detail, but I'll just mention this. This is a prosthetic eyeball. It was made from coral, calcium carbonate, but was replaced by apatite. And what's amazing about this is because it's apatite, and when it's put into the ocular cavity, it's recognized by the body, and muscle will grow into it, and it will eventually track with your good eye. I think it's just an amazing example of the types of things that are happening today in biomaterials.
Thank you, John, and I'm delighted to be here today, and I'm delighted that everybody is here. I'd like to thank C2/M Mineralogy. I gave an early incarnation of this talk to my crystal chemistry class this spring, and one of the students asked if there was a speaker for every space group, but I assured him there wasn't. You can imagine being the P6 sub 5 distinguished speaker. It would be a tough one. What I'd like to do, I love space group jokes. I'd like to start today by talking about MSA, and the MSA is really nothing more than people. We were started by Edward Krauss, who was the first president, and our list of presidents here. In 1937, we started awarding the Roebling Medal, and Charles Palachi won the first one, and we saw him in an earlier picture yesterday. No awards were given for the Roebling Medal in World War II. But in 1948, the Roebling Medal was awarded to the first of 2 Nobel laureates, Sir William Lawrence Bragg. In the 50s and early 60s, many of the scientists whose work I read as an undergrad 20 years later were the officers and Roebling Medal winners of the Society. In 1967, Linus Pauling won the Roebling Medal. He won 2 Nobel Prizes, but I'm sure the Roebling Medal meant much more to him than those. Don Bloss was president in 1977. It was wonderful, Mickey, that Don could kick this off. Don is the oldest living president of the Mineralogical Society. In 1989, the first female winner of the Roebling Medal, Helen McGaw. Many of you who attend the Tucson Gem and Minerals Show may know Peter McGaw, who is her cousin. He's a geologist and one of the organizers of the show. In 1993, we had our first female president of the society, Alex Navratsky, and Alex and I were reminiscing about her presidential address yesterday, and she later went on to win the Roebling Medal. In 2000, one of my grad school mentors, Bob Reynolds, won the Roebling Medal, and in 2008, Peter Heaney was president. Peter, who's one of the organizers of this wonderful symposium. Steve Shirey, the other organizer, was president in 2015, and that brings us up to today in Mickey Gunter. But the society is much, much more than the presidents and the Roebling medalists. And thank you to everybody who's been a part of the society. And I'd like to say a particular thank you to Alex Spear. Everybody knows how much Alex means to the society, and as he looks towards retirement, I want to thank him especially. Alex has been a good friend, and when I was nominally president, he ran the society. You've probably seen over many years, I've given talks on the crystal chemistry of apatite and the steric chemistry of the anions, the apatite anion column. But today's not about that. I'd like to give a very brief primer of the crystal chemistry, but we're going to talk about the societal relevance of apatite. Apatite crystallizes in space group P6 sub 3 over M. That's its formula. We'll divide it into two separate calcium sites for something I'll mention later on. But apatite is very important to us because it is the source of phosphorus. Phosphorus is very important to us. It occurs in the crust at about 1,000 parts per million. It is essential for life. It's the backbone of DNA. Our bones and teeth are made up of apatite, and Jill will talk about those in the second talk. Apatite is found in igneous rocks, metamorphic rocks, sedimentary rocks, hydrothermal deposits, usually in accessory and trace amounts. As I was learning petrography as a geological neophyte, I remember being told that you're not finished describing a rock until you found the apatite, those tiny little grains, because invariably they were there. The rock always had that 0.13 weight percent phosphorus in it, and it always went into apatite. Apatite is the major source of phosphorus on Earth, usually from phosphorites, and that's where we as a society consume our phosphorus. This is the apatite atomic arrangement. I won't dwell on that today. And as I said, I spend a lot of time with John and others looking at the arrangements and stereochemistry of the anions in the anion column and the different compositions, etc. And for example, how do fluorine and hydroxyls interact in our teeth and issues like that. But apatite is also used in many geologic applications as well. Uranium substituting in the apatite structure will spontaneously fission and create tracks in apatite that we can actually count, and it'll teach us something about the rates and dates of geologic processes, and a lot of work goes into doing that. Apatite is very important for the control of rare earth variation in rocks. Our recent Roebling medalist, Bruce Watson, spent a large part of his career looking at the diffusion of rare earth elements in apatite, and the partitioning coefficients of rare earths in apatite are so high that in many places we actually mine apatite for the rare earth elements, and I think of Mineville, New York. Apatite is also a recorder of planetary processes. We heard that this morning from Hap McSween, talking about how it recorded the volatiles in the Martian meteorites. Apatite provides a fingerprint of metasomatic processes. I suspect many of you use it for that. Apatite is used extensively in geochronology and thermochronology and has for decades in geology. Apatite is a recorder of magmatic processes, and we use it for that. And there's many, many other uses of apatite that are germane to today's society. And that's what I want to focus on today, a bit unusual of a topic. I'd like to say that you'll hear it here first, but in 2016, there was a lot of talk of politics, and I predict in 2020 we will hear the same thing. And it's actually very interesting because in 2016, my senator, Bernie Sanders, declared in his campaign that the major problem facing humankind today was climate change. And this was actually significant because it's the first time that a geologic matter was named as the greatest political challenge facing humankind. And I think we should remember that. But unfortunately, Bernie got it wrong, because if he had read the yearbook of the World Watch Institute about 35 years ago, there was an article that stated the gravest problem facing humankind is the impending lack of appetite. The gravest problem facing humankind is the impending lack of appetite. And I'll explain why that article was written. But it brings us to the topic of minerals and society. We talk about many different aspects of minerals. We look at minerals in every different way, and I'm one of them. But we should stop occasionally and look at how minerals impact society. And I'll use an example of my trip down here. I actually didn't come from Vermont. I came from a different direction. But if I had, I would. I live in Vermont, so it's not that odd. If I would have come down here to this meeting from Vermont, I would have hopped on a plane in Burlington at the Burlington International Airport. The entire trip today would take me 4 hours from door to door. And I'd get here and I'd call my wife and I'd complain and say the landing was rough and I didn't get upgraded. And think about that. To travel from there to there takes 4 hours, and we complain about it. So let's go back just 200 years. We're looking now at 100 years since the start of the society. Let's go back and look 100 years before the start of the society. What would a conference have been like in those days? And I got the latest date last night from John Valley. The Earth is 4.567 billion years old, and we're looking at 200 years. And John would kill to have an error bar of 200 years in 4.5 billion years. So keep that in mind, how short a time this is. So what would it have been like if I was lecturing in 1819, 100 years before the MSA? I would have had to travel 842 miles, and it would have taken about 3 months. This is only 200 years ago. I would have had to leave on March 21st. I would have had to walk or ride an animal. There would have been no water systems along the way. There would have been no food distribution systems, what you would kill what you want to eat. There would have been no sanitation systems. There would have been no communication systems. I couldn't call someone on my cell phone and say I'd be a little late. If I stopped at an inn, there'd be no air conditioning. Heating would be by wood. There would have been no electrical systems. There was no power generation system back then. If I wanted to work at night, obviously I wouldn't have a computer, and I'd have to work with light from a candle, and probably the most impactful of all, there would be no internet. But think about it. We find humor in this, but this is only 200 years. And what has changed in society, and what has really changed in society, is our extraction of minerals and the role of minerals in society. And this all started to change in 1859 with the discovery of petroleum in Titusville, Pennsylvania by Colonel Edwin Drake. And the invention of the gasoline-powered internal combustion engine in that same year, and perfections made to that in 1876. Suddenly, for the first time in the 4.567 billion year history of the Earth, humans became a geologic agent. And that's what enables me to fly down here in 4 hours and complain about it, rather than ride a horse and take 3 months to get here. And we've all seen the bumper sticker that said, if it's not grown, it's mined. And everything around us either is extracted from the earth. I think of the number Mike gave yesterday, 350 billion tons, 350 gigatons that we extract every year that allow society to be what it is today, and so different from just 200 or 150 years ago. And the reason apatite is so important is its role as a fertilizer. We as a society like to eat, and to grow the food resources that we need, we must use fertilizer. And one of our main fertilizers is phosphorus. And whenever you buy fertilizer, you're buying phosphorus. This is an old Department of Agriculture photo showing what happens when you try to grow food and you don't fertilize, and this is what happens when you do fertilize. We can go back, and those books we saw when we were in grade school, and the Native Americans showed the Pilgrims that if you put a fish in a hole where you plant your corn, it'll grow much better. And what we know now is you are just using apatite for the phosphorus. And in fact, if you go to any plant store, you can buy fish bone meal, and that's a good fertilizer. You're merely adding apatite to your plants for fertilizer. If we look at the human consumption of apatite over time, it's been rather dramatic. Remember, this is only about 100 years ago where we started, and in 1900, humans consumed essentially no rock phosphate or apatite. But in 1900, there were basically 6 people on Earth. There were my 4 grandparents and Adam and Eve. And we simply didn't need that to fertilize the Earth. But over just 100 years, we've grown to where we're mining 200 million tons per year just to feed the Earth. We can look at how population has changed with that, and when we do, we see a very dramatic coincidence between the amount of apatite that we have consumed and human population. We cannot grow the human population without feeding them, and that's what it takes. We have to have that apatite. And in fact, the worldwide average, each of us consumes about 20 kilograms per year of apatite just by being a citizen on Earth. And that's not the entire case, because if with our bovine-based diet and our ethanol production, we in the U.S. consume a lot more. And if you think about it, in the U.S. population, we have 1 birth every 8 seconds, 1 death every 13 seconds, 1 international migrant every 29 seconds. We gain 1 person every 12 seconds, and during the time of Jill's and my talk, somebody has to find 12,000 kilograms of apatite to feed the new people coming into the United States. No longer can we mine like this. We have to go to large-scale mining. But what change has that had on Earth? If we go back to 1790, we can see that 90% of our U.S. population were farmers. It took that 90% to feed themselves and the other 10%. Now, this isn't only apatite and fertilizer, but mechanization. You can't carve a tractor out of wood. We can see that we've seen a dramatic decrease in the percentage down to 1.5%. And if we look at it today, that means we've freed up 88.5% of our population in the past 200 years. And what do those people do? They do everything from A to Z. They're astronauts, they're geophysicists, they're movie directors, they are rocket scientists, all the way down to X-ray crystallographers and Zika virus researchers. These are occupations we have today we didn't have 200 years ago because virtually everybody was a farmer. How long will it continue? We don't know. Yesterday, Gordon talked about the problem of predicting resources, and one concept I've always loved as a geologist is estimating the amount of a resource yet to be discovered. Peak apatite, this researcher gives about 2030. We don't know when it'll be, but we know that the first sign of reaching peak production of some commodity is price instability. And this is the prices for rock phosphate. And we know this was predicted in 1972. It was interesting. Gordon showed a picture of the limits to growth that Dennis and Danella Meadows wrote and predicted our change in resources. That has, everything in there hasn't been shown to be true. But keep in mind, this was done because it was the first time we had computers large enough to make these estimates. And this was less than 50 years ago. How else do we use apatite? We use it in PIMS. We use it for phosphate-induced metal stabilization. Here's a picture of pyromorphite that'll become clear. If we have contaminated water contaminated with lead, cadmium, or zinc, we can have it flow through a permeable reactive barrier, which is nothing more than fish bones or apatite. And in this case, we can show where there's lead in the water, it will actually precipitate as pyromorphite on the fish bones. And this has shown in the last 20 years to be a very effective way of cleaning water using PIMS, not only for things like lead, but in the Hanford nuclear waste, or Hanford nuclear reservation, there's a lot of strontium-90 in the groundwater, and we can use PIMS. And in fact, the groundwater flowing into the Columbia now is very, very clean because of PIMS. It's being flown, or it flows through a permeable reactive barrier of apatite that cleans it up dramatically. We also use apatite in our lighting. We've been walking around under apatite. It lines the tubes of the lights, or at least it used to. We can change the composition of the apatite to give us different wavelengths. That became too expensive, and we moved to triphosphors coating the tubes, but the triphosphors are merely, the phosphorus is merely obtained from apatite. We can make designer lasers by putting dopants in either CA1 or CA2 site, and we can do that by co-doping with other things, and John and I have worked on patents in that process earlier in our careers. We can encapsulate nuclear waste. We can make uranium fluorapatite, and we can put the uranium in apatite, and then we have a solid state repository for radioactive materials, and we can encapsulate it for a much longer time, isolated from the biological environment, and we can even make gemstones. And I hope many of you saw Monica Rakovan last night wearing her beautiful 10-carat apatite stone last night, and she wore it so I could refer to that today. So, and those are just the inorganic requirements. Apatite can teach us about rates and dates, rare earth elements, planetary processes, on and on and on. Allows us to grow population from fertilizer, clean water, gives us lighting, sequesters radioactive waste, and gems. But now I'm going to turn it over to Jill, and Jill will show us that apatite can, and this is true, can even help detect cancer, and what the Centers for Disease Control considers one of the 10 greatest public health achievements in the last decade has come from bioengineering of apatite. So we've only just begun. Thank you very much.